Welcome back. In this lesson, we're going to be looking at the syllabus point A1.1.4, explaining the purposes of different types of memory. We're going to be looking at registers, cache, random access memory, and read-only memory. Now, primary memory serves as the central workspace for the CPU, often facilitating the storage and quick access of data and instructions which are still in active use. So the programs that you want to run, they are loaded into RAM. And it can be volatile, which means that it requires power to maintain the stored data, which is the case in RAM, or it can be non-volatile, which means it retains information even when the power is turned off. So SSDs, HDDs, and ROM, read-only memory, are non-volatile, whereas RAM and cache are volatile memories. So let's start by just looking at what primary memory actually is. Now we know that a computer is just hardware and it uses electricity to operate. Now without memory, we would need to enter a program sequentially followed by the inputs that we need every time to get an output. There would be no storage, there would be no referencing back to previous instructions. Therefore, a computer requires a space where it can store data and instructions so it can reference to it as many times as it needs. So primary memory is the fast temporary memory that stores data and instructions that the CPU actively uses while the computer is running. And these memory types are often volatile, meaning their contents are lost when the power is turned off, with the exception of ROM, which is non-volatile. Now, SSDs and HDDs, they are called secondary memories. They are not primary memories. Another distinction for primary memory is that it is directly accessible by the CPU. It doesn't need to go through an intermediary. So therefore, the CPU can directly access ROM, RAM, cache, registers. Therefore, all of these are classed as primary memory. So let's start looking at the different types of primary memory. We're going to start off with registers. Now, registers are built directly into the CPU. They're the fastest and smallest type of memory. They're actually on the processors. Generally, you will be storing bits or some bytes in this type of memory. They store data, instructions, or addresses being used right now by the CPU. So they will not be storing anything that is for the future. It is just what's needed right now. And you already know certain examples from previous sessions: accumulator, program counter, instruction registers. All of these are type of memories. Now do remember, registers are volatile memory, therefore data is lost if the power is turned off. Next up is cache. Cache memory is small but provides high-speed access to the CPU compared to RAM. It acts as a buffer between the CPU and the slower RAM, storing frequently used data and instructions. And there are different levels of cache: L1, L2, and L3. Each of these have different sizes and speeds. The closer a cache is to the CPU, the faster it is. Level 1 cache is located directly on the CPU, making it the fastest type of cache. It can be accessed almost immediately due to its location. However, it is also the smallest, often a few kilobytes in size. And each CPU core usually has its own level 1 cache, which is typically split into two sections: L1I to store instructions and L1D to store data. So there could be two L1 caches for instructions and data. L2 cache can either be on the CPU like L1, or it can be situated very close to the CPU, and generally it's larger than L1 and can be up to several megabytes in size. It stores frequently accessed instructions. It's faster than L3 but slower than L1. Now L3 cache is the slowest of them all. It's the furthest away from the CPU but still close enough compared to RAM. Another benefit of L3 cache is it can be shared across multiple core CPUs. Now L2 cache can also be shared, but generally L2 cache can be specific, just like L1, to a particular core. However, it could be shared if the designer allows that to happen. L3 is always shared. Now L3 cache is the largest of the three, often in tens of megabytes. And just like all the others, L1, L2, L3, they're all volatile memory storages. Therefore, they lose data when the power is turned off. Now this is a good place to talk about cache hits and misses. A cache hit occurs when the CPU finds the data it needs in the cache. Therefore, it gets on with the processing really quickly. A cache miss occurs when the data is not in the cache and must be fetched from RAM or further, and this results in slower access. Most modern CPUs use prefetching, replacement policies, and spatial or temporal locality to improve cache hit rates. Now think about it this way. I've got 10 instructions. I'm loading instruction number 1. And what happens is the 10 instructions are loaded directly into the cache, so the CPU doesn't need to go to the slower RAM every single time. So it accesses instruction 1, and then it needs instruction 2, which is already in the cache, so therefore it doesn't need to wait for too long. Now what happens is that when it goes to instruction 2, that's a cache hit. The data is already in the cache, or the instruction is already in the cache. However, what happens from instruction 2 is there's a jump which goes to instruction 12. So that instruction is in RAM and it's not currently in the cache because we only loaded 10 instructions. Therefore, that's a cache miss. The CPU will now need to empty the cache, go back into the RAM, load the next 10 instructions, bring them back into the cache, and then it will be able to access it quickly. And that results in a slight delay because you're clearing it, fetching more data from RAM, and loading it into the cache. The next type of memory we're going to be looking at is the main memory, often known as RAM. Now, RAM stands for Random Access Memory, and it's the primary workspace of the computer. It temporarily stores the currently running operating system, processes any active data, instructions that are required. It is a volatile type of memory, and its capacity is measured normally in gigabytes. Now, if you're using 16 GB of RAM, that would be adequate for multitasking, maybe a bit of light gaming or content creation. Whereas anything over 32 gigabytes of RAM would be ideal for power users, and this is valid in 2025. Some supercomputers obviously go into terabytes of memory. However, for most everyday purpose computers, we're looking at maybe 32, maybe at max 64 GB of RAM in 2025. Now, the next type of memory we're going to be looking at is read-only memory, which is a type of non-volatile memory. And that means that data isn't lost once the power is turned off. Now, this is used to store essential instructions and data for the computer, especially when it needs instructions for startup. So BIOS, or basic input output system, or firmware that is stored in ROM. So data in ROM is typically not modifiable either during normal computer operation, although you can modify it via special processes when you want to, say, flash your ROM or upgrade it with a new firmware. ROM's role is primarily for firmware storage and is not directly involved in the day-to-day memory access hierarchy involving registers, cache, and RAM. So when the user wants to use a program, chances are registers, cache, and RAM are being used. But when you want to start up your computer, ROM is going to be used. So it's better to consider this as a completely separate entity which focuses on system boot up and low-level startup operations. Now, a key term that you need to remember here is latency. And latency is the time delay between the transmission of data and its reception. Registers have low latency. L1 cache has low latency. RAM would have very high latency. So you should be aware of the hierarchical structure that's used in a CPU's interaction with memory. The memory access order is registers, cache, L1, L2, L3, RAM, and storage. So data is loaded from the storage, goes into RAM, then L3, then L2, then L1, and then into registers, and then the CPU can access it. Now, often you will get a question where the question asks, how does the CPU access data? In that particular case, you need to say that the CPU first checks the registers. If you can't find the data in the registers, it will then check the level 1 cache. If you can't find it there, it will then go to L2 and L3 cache. Then it will finally go to RAM. And then if it's not in RAM, it will need to be loaded up from the storage. This particular process reduces latency and increases speed by avoiding the slow RAM or storage unless it's absolutely necessary. Now, there are a lot of key terms involved in this particular lesson, so there's few that you see on screen. Make sure you pause the video and go through them. Make sure that you're actually aware of cache hit, cache miss, and latency. They're quite important. The rest of them are pretty standard. And that leads us towards the end of this particular lesson. On screen, you will see a few practice questions. Hopefully you can now answer what the primary differences are between RAM and ROM. Why does a CPU use cache memory? What is a register and why it's important? You should be able to define a cache hit and explain why it is beneficial. And you should be able to arrange from the fastest to slowest primary memory types on screen. So L2 cache, RAM, register, L1 cache. Can you put them in the right order from fastest to slowest? That's all for this particular lesson. If you do have any questions, please get back to me in the comments. Otherwise, I'll see you in the next one.